Yeah.
Okay, thank you. Good morning, everyone. My name is Ali, and I'm doing a postdoc in Technical University of Denmark with the topic of microadditive manufacturing and process chain. The outline of my presentation is the state of the art, the background of the study, the additive manufacturing with VAT polymerization method mainly, and the experimental procedure, measurement analysis, result, and finally the conclusion. In 2012, the additive manufacturing were categorized into 7 different areas. The material extrusion, fuse deposition modeling, which is FEM, and then material jetting, polyjet, the binder jetting, which using some printer by powder and then bind the powder together, and then sheet lamination for the sheet forming, and VAT polymerization, which is the main topic of this study, is stereolithography and digital light processing. And then powder bed fusion, selective laser sintering, and finally directed energy deposition by using a laser or electron beam which is focused to melt the material and then bind them together. And then as you probably know, additive manufacturing, like many other processes, have some disadvantages and advantages. The advantages such as rapid prototyping, design for additive manufacturing for their lightweight component, flexible product development, no tooling is required, and then ability to respond to specific customer need by customization of the product, and then finally the tool for the other processes, which this topic is mainly the one that I'm working on it. We use the additive manufacturing as a tool for the other process such as injection molding and extrusion. And then disadvantages, the cost, particularly the metal, which is quite a costly part, and then the initial cost of the machine is quite high, and the need for the post-processing. I would like to highlight the need for the post-processing because it's somehow a game changer in additive manufacturing if we cannot apply this post-processing correctly. And finally, the precision and part integrity. Here is an interesting comparison in different manufacturing technology that you can see in the polymer and the metal material. This comparison assumes that the best case of the build parameter applied for each manufacturing process. As we can see here, the VAT polymerization method is quite good dimensional accuracy compared to other manufacturing process. And we can compare it with injection molding and high precision milling as well. Just to go back in some other study, we can see for manufacturing this kind of micro component, we have different procedure to apply for making this kind of component, which started from CAD design of a structure, then E-beam lithography, mask fabrication, X-ray lithography, electroplating of the mold, and then replicating but hot embossing. Then finally get the final product. This is the example of fabrication of the lotus structure. The other components such as the gecko toes, which use the conventional 3D printed master dip, which also contain different procedure and also very time consuming method to make this kind of hierarchical structure. However, we applied directly 3D printing in our previous study, and we can get this kind of a structure, which is the mushroom shape with the neck of 50 micron diameter and the top diameter of 100 micron, which after tuning the parameter, we could reach this kind of structure directly about 1 hour manufacturing time. This is the SLA method setup that for this study we use the Formlab 2, which contain a build plate, the elevator, and the VAT. The bottom of the vat is transparent, and we use the unpigmented resin for this study, and the laser is used for curing the part. For the other method that we use is the DLP. This is the setup of DLP. They have more or less the same setup, but in this one, we just have a projector instead of the laser. The same setup. This machine was built in additive manufacturing lab of the DTU, and if I can play this video, I think you can easily understand. No, how it works. Yeah. No? Just a moment, I think, yeah. Okay, I just skip it. I just wanted to show that how the projector will just uniformly project the light on each layer, each selected layer that we want to make and make the feature. And the feature will be placed mainly on this build plate. And then the detail of the projector, it's a 1x magnification projector, and the printing area is 20 by 11 millimeter square meter, but it's kind of a trade-off. If we want to have a bigger printing area, we have to magnify, and then we have a bigger spacing of the pixel, because the pixel spacing here is 7.6 micron, which is placed on this micron mirror inside the projector, and all this mirror will be project the light selectively. And then we will get this quite limited printing area. However, we already tried different magnification lens, but we cannot get such a resolution with that higher magnification. Here is the post-processing. As I mentioned, the post-processing is quite challenging because we have mainly two sections for the post-processing. The first one is the part cleaning, and then we have the post-curing. For the part cleaning, because the leftover resin is all between the feature which is printed, and it's upside down on the build plate, and it's just sink inside the whole resin. Then we need the isopropanol to remove it with the ultrasonic bath, and it's about 15 minutes to put it in the bath and then remove the leftover resin. Then we apply gently the pressurized air, and then dry the sample and make sure that there is no resin in between the features. And then finally, the UV curing oven, about 15 minutes to cure the whole part. For this study, we used two different sample geometry, and then the hollow box and the hollow cylinder. And in form of a matrix, the sticks are identical, and then with decreasing aspect ratio of 0.75. We try to let's say start from 1.5 millimeter, and the smallest one is 6 micron. And we tried how it will be printed for the SLA machine in terms of geometry and size, and we evaluate these two. And then 5 samples for each of them were printed and then evaluated. Here is the result from the DLP. We use different condition and parameters such as layer thickness, exposure time, film thickness, and the geometry. And then in a full factorial experiment, we try to analyze the contribution of each parameter in this experiment. And as you can see how the results were improved from this geometry, which all stuck together, and then we got a much better result by improving the parameters. This is also for the mushroom shape result. As you can see how it's all merged, and the level are all the same. And it's improved, and we got the final result like this. This is the parameter that we use for the SLA method. The layer thickness was 25 micron, and then 35 degree the temperature of the print resin. The Alicona Infinite Focus 3D microscope was used for the measurement of the feature, and the SPIP software to evaluate the result. The circularity and squareness mainly was checked for the printed features. And then apart from that, the uncertainty evaluation procedure was applied based on the ISO standard with the coverage factor 2, which expand the uncertainty, which is 95% coverage of the whole printed samples. The temperature effect was not considered because the measurement applied in a standard room with the constant temperature. And then finally, repeatability and reproducibility of the additive manufacturing machine was considered. This is some result with the poor post-processing. As you can see how it will be affected, and the final part we have poor result out of it. The other effect of the post-processing is in the hollow component. and it's very difficult to remove the leftover resin from the component. Apart from the pixel size and the voxel that we have for the printing, mainly for the wall thickness, we have also this difficulty to remove the resin out of it. These are also some results with the poor post-processing, as you can see how the resin will be stuck there. And this is some result with a bit better, and we managed to remove the leftover resin there. The other problem that we have is the high aspect ratio feature, which we have a failure in the high aspect ratio feature. As you can see here, in 500 micron height, the feature are quite good printed, but in 2 millimeter height, they start to be bended, and we have failure in high aspect feature. This is also because we push a bit post-processing, and then it just affects these tiny pillars. This is the main result from the SLA, which we can see also up to the fourth column. We have the hollow square and hollow cylinder, and the rest it's all filled with the resin, and we cannot go beyond that. And this is also other result. In terms of the geometry, with the corrected geometry, the fourth column was printed for both boxes and cylinder, which the width and diameter of 632 micron, and the smallest print was 6 column and 14th, which was the geometry of 335 micron and 35 micron for the cylinder. And here also we can see the thickness of the layer with the higher magnification, which was 25 micron. And this is the result of the roundness and the squareness. We had, let's say, a more uniform result in different batches for the squareness instead of the roundness. In roundness, we have a bit of variation in each batch of print. Then finally, in terms of the uncertainty, it was 11.25 in the z-axis contribution mainly for the hollow box, and 14 for the cylinder in micron. Then to conclude, just the performance and the capability of SLA machine has been evaluated, and different test parts were used. 5 different samples parts have been printed, and the samples were measured and the results were analyzed with different process parameters. The repeatability and reproducibility of the machine were evaluated, and the expanded uncertainty with coverage factor 2 were calculated, and the roundness and squareness of the sample were evaluated. And at the end, just acknowledgement from Technical University of Denmark and Marie Curie Foundation for funding of this project. Thank you.
Thank you very much.